Thank you very much. And well, it is a great pleasure to be speaking at this conference, and apologies obviously for the remote format. So I wanted to talk about the program that we launched some years ago with Reshetikhin and Cattaneo about putting kind of together the Batalin Vilkovisky formalism for perturbative path integrals for gauge theory, together with a functorial picture of a T and Siegel with gluing and cutting of the space-time manifold. So, the plan is like that. So I wanted to just very briefly talk about Batalin Vilkovisky formalism and advertise a little bit the idea of Wilsonian effective actions in BV context. And then we'll transition to this context with boundary, with gluing and cutting, which is dubbed, well, by this awkward name, BV-BFV formalism, but there's some reason for that. Then sort of, well, applications in some sense. So, well, examples. So how it works in the case of a special subclass of so-called AKSZ topological sigma models, special subclass, which we call BF-like theories. And then an example of two-dimensional Young-Mills with corners and how you can sort of using this formalism obtain, finally compute all Feynman diagrams and using cutting and recover the representation-theoretic formula for the partition function. And finally, I wanted to mention an application to the effective action of Chern-Simons theory on a cylinder and relation to Chern-Simons to WZW, Vesumin-Witten correspondence. All right. So just a sort of one slide recap of Batalin Vilkovisky formalism. So what is it about? So on the level of classical field theory, the structure is just a certain supergeometric package. So there is a space of fields, which is a graded supermanifold. So for a bosonic field theory, it would be Z graded with sort of superstructure. So the data which coordinates are commuting, which are anti-commuting, coming from mod 2 projection of the Z grading. So equipped with an odd symplectic form. So convention is that its degree should be -1, and equipped with an action of degree 0, so a function on the space of fields, which should satisfy the one kind of structure condition that the Poisson bracket of action with itself is 0, which is called the classical Maastricht equation, which in particular implies that the Hamiltonian vector field generated by the action is squares to 0, so is a homological vector field. So it's an object of degree +1. So a vector field on F of degree +1, commonly called Beresty operator or Beresty operator in BV context. So that's kind of the classical structure. And kind of the idea of quantization is that we are interested in the integral of the exponential of the action over a Lagrangian inside the space of fields. And well, we are free to choose this Lagrangian as long as we can make sense of this integral by, well, formal stationary phase formula. So this choice is a choice of gauge fixing. And provided that as the action satisfies some kind of improvement, refinement of a Maastricht equation, namely this so-called quantum Maastricht equation. So delta here is a canonical second order differential operator on functions on F coming from the symplectic structure. So odd second order differential operator. So we want the integrand to be killed by this BV Laplacian, the second order differential operator, which is equivalent to this version of Maastricht equation where we add to the Poisson bracket the term with delta of S. So provided that this happens, that S satisfies the quantum Maastricht equation, then this integral doesn't depend on a deformation of the gauge fixing Lagrangian. well, at least, so in the context of finite dimensional integrals, this is a version of Stokes' theorem. For path integrals, well, this is sort of a hope which has to be made precise by first converting everything into, well, I don't know, Feynman diagrams, for instance, and proving this on the level of Feynman diagrams. And of course, one can also cast observables in this formalism and consider not just kind of the full integral, which would be the partition function, but also put in some observable inside, and provided that this function on the space of fields is annihilated by this differential, which is the PRST differential with some correction, well, then again, the result doesn't depend on the choice of Lagrangian. So that's BV formalism in one slide, some kind of quick recap. And well, a refinement of this formalism is effective actions. So this is kind of an adaptation of Wilson's idea of an effective action. So instead of integrating over a Lagrangian in the entire space of fields, we want to split the space of fields into a slow part and the fast part. So slow part, well, one could call them infrared and ultraviolet, or one can also like to call the slow part residual fields. And we don't have a name for the fast part, just the fast part. So then the picture is that we would like to choose a Lagrangian in the fast part and integrate over that Lagrangian kind of while keeping a point in the slow part as a parameter. So this is the picture. So the space of fields is fibered over the slow fields, with fiber being this dashed part, the fast fields, and we are integrating over a Lagrangian inside the fast fields, and we are sort of moving this fiber along along the residual fields and seeing how does the result depend on that point. And well, denoting the result of this fiber integral, the exponential of something, this something is called the effective BV action. Okay, so now this construction has some properties. So one property is that provided that S itself satisfied the master equation, then the effective action will also satisfy the master equation, which you can also write that like, well, the BV Laplacian of this result is killed by the, sorry, this object is killed by the BV Laplacian. And if I change my gauge fixing Lagrangian L, then effective action changes by a canonical BV transformation. So appropriate version of the action of a symplectomorphism here. And on the level of this Z, it's just a shift of Z by an exact term with respect to the BV Laplacian. All right. So now there are lots and lots of examples around of effective BV actions. I just wanted to give my favorite example. So it goes like that. So if you're looking at a one-dimensional field theory on an interval, so it's a very simple example, it's one-dimensional field theory. So you fix some Lie algebra of coefficients. You look, I'm sorry, it's a bit of a dense slide. So, but so the space of fields is two copies of differential forms on the interval. One copy with coefficients in the Lie algebra, one copy with coefficients in the dual, some degree shifts. So we call first differential form A, the second differential form B, and they're both non-homogeneous differential forms. So then there is the symplectic structure that just coming from, well, the integral of the wedge product. And the action is so-called non-abelian BF action. So it's the integral over the interval of B wedge dA plus half bracket of AA. This is pretty much the formula for the curvature of a connection, but here A, instead of being just a connection, it's actually a sum of a zero form and the one form. And B is also a sum of a zero form and the one form. So now, okay, so that's kind of the classical data. And the space of residual fields here, I wanted to be cochains, cell cochains of the interval with this standard cell decomposition, two endpoints and the bulk cell. So cochains with coefficients in the algebra plus chains with coefficients in the dual with some appropriate shifts. Then there is chain contraction of, a deformation retraction of differential forms to cochains, to cell cochains, given by triple of maps, the inclusion of cochains into differential forms by Whitney forms, so linear zero forms and constant one forms, the projection by integrating over cells, and a certain explicit simple chain contraction, chain homotopy operator acting on differential forms. So contracting differential forms onto the image of cochains there. So there is this these three maps that give you the data of deformation retraction. So using these three maps, one can construct the splitting of the fields into slow and fast ones, or the the slow and the fast ones, and a Lagrangian inside there. So the Lagrangian essentially is constructed in terms of this chain homotopy. So, and then, one can just write down that fiber BV integral and compute it by the stationary phase formula with kind of corrections given by Feynman diagrams. So it's ultimately a Feynman diagram computation, and a simple one at that. So there will be some kind of diagrams like this, like branches, and some diagrams which look like wheels, and that's it. And I should mention that the edges in these diagrams are decorated by the chain homotopy. And the leaves are decorated by this residual A field, so the cochain field. So A but the cochain version, and the root is decorated by the chain B field. And I just wanted to write down the full answer of this computation. It's kind of a neat one. So when you do this computation, you obtain some. There are some integrals that need to be evaluated, and they give you Bernoulli numbers for some reason. And so this effective action has this form. So A0, A1, A01 are just the components of this cochain. B0, B1, B01 are the components of the chain. So this is a function on the finite dimensional space, on this finite dimensional space. And it has these Bernoulli numbers, they assemble into some trigonometric functions. So, this action, it satisfies the master equation. And also it has a neat sort of interpretation that one can see this action as a generating function for a certain algebraic structure on cochains of the interval, cell cochains of the interval, with coefficients in the Lie algebra, namely the tree part of the effective action generates an L-infinity structure there, so a sequence of L-infinity operations, and the quantum part generates some additional polylinear operations, and they are also linked to the classical L-infinity operations by some quadratic relations, which are a part which are also generated by the quantum master equation. And one can view the process of computing the effective BV action as a homotopy transfer from the de Rham algebra of forms with coefficients in the Lie algebra to this interesting algebra of cochains of the interval. Okay, so I just wanted to advertise this example because, it is an example of an effective BV action, and with this neat algebraic interpretation. And its sort of direct generalization is that instead of an interval, I can consider any manifold equipped with a triangulation, and I can consider the action with space of action given by the same formula as before, but with integral over M instead of the interval, with fields being just pairs of differential forms, and the residual fields being again a cochain of a triangulation plus a chain on a triangulation. Then one can write down some formulas for the effective actions. The effective action, they are a bit less explicit, but still kind of meaningful and interesting. And the effective action is actually a sum of certain universal building blocks for the simplices of triangulation. And the picture here is that, you have your kind of theory on differential forms, the original one. You have this induced effective theories on various triangulations. And if you have a more dense triangulation and a more sparse triangulation, you can jump from the more dense to the more sparse one, also by, again, by a fiber BV integral, by an effective BV action, by integrating out the redundant fields from here. And also from each of them, you can jump to sort of the smallest model for residual fields, which is given by cohomology of X with coefficients in the Lie algebra plus homology of X with coefficients in the dual. And you read off some kind of interesting topological invariants here. So you obtain some effective action, which generates some unimodular L-infinity algebra on cohomology, which contains interesting topological data on the original manifold. Okay, so now that's what I wanted to say about kind of BV and without boundaries. And now this refinement to gluing and cutting. So this is the slogan that, well, what we want to do is put together BV integrals with ITS-Siegel gluing and cutting. And well, the result is dubbed BV-BFV formalism. And on the classical level, it's again, some kind of supergeometric package attached to the bulk manifold M and some supergeometric package attached to its boundary, which I call sigma. So the packages are like that. So I don't know, this is a picture of a manifold with boundary. And okay, the packages are like that. So we have a space of fields, which is again a graded supermanifold, Z-graded supermanifold for the bulk, equipped with a homological vector field Q, equipped with a odd symplectic structure, again of degree -1, equipped with an action and a projection to the boundary fields. So this is a projection to the boundary fields, and to the boundary we assign its own space of fields, which is again a graded supermanifold equipped with a homological vector field. And there should be a symplectic form which we assume to be exact. So it's D of some one form, and equipped with then some action of degree +1, which we call BFV action. So this condition that the symplectic form is exact can be relaxed. Instead, it can be more like asking that it's a curvature of a connection in a pre-quantum line bundle. So you can relax this condition. Okay, but let me sort of use this version. And the structure relations are that, well, these vector fields are indeed cohomological. They are linked by the projection. So the bulk Q is projectable, and the projection is the boundary Q. On the boundary, I want this BFV action to be a Hamiltonian for the boundary Q. So this is the relation. And in the bulk, well, not quite so. So S is not quite the Hamiltonian for Q. Instead, this relation of being Hamiltonian is being spoiled by a boundary term. And the boundary term is precisely given by this boundary one form. So this is the main kind of structure relation in this package, linking the boundary data and the bulk data. And so there are kind of several consequences here, and one consequence is a version of classical master equation with boundary, and it says that well, Q of S is some boundary term, a pullback of something that you can construct in terms of the boundary data, and morally it measures sort of gauge non-invariance of the action and kind of the failure of gauge invariance coming from the boundary. So one has also kind of gluing in this picture. So a gluing of two bulk manifolds over some kind of interface sigma corresponds to a appropriate notion of fiber product of these supergeometric packages, of bulk packages over sort of the interface package. All right. So and the simplest example here is abelian Chern-Simons theory on a three manifold with boundary sigma. So here, well, the bulk fields are just, again, non-homogeneous differential forms with, well, homological degree shift by 1. So again, the symplectic form is just the integral of dA wedge dA. Oh, I should call delta the Ram on the space of fields, as opposed to D, which is geometric Ram operator on the manifold M. So this is delta in the symplectic form. And the action is just the usual abelian Chern-Simons action, ADA, but we need to remember that A is a non-homogeneous differential form. And the homological vector field, or BRST operator, is the lifting of the RAM on M. And the boundary data is given by essentially the same formulas, very similar looking formulas, except that kind of replacing M with sigma. So in particular, all integrals are over the boundary, which in particular shifts the degrees of those objects. Because that means that here we are integrating a two-form part component of this product, whereas here we are integrating three-form part component. And the projection is just a pullback of the form to the boundary. So this is this classical BV-BFV data in this example. And it also has an interesting reduction. And well, you can consider it for any gauge theory that you have cast into this BV-BFV formalism. So in the bulk, one can consider, well, physically speaking, those would be solutions of equations of motion modulo gauge symmetry, and on the boundary, solutions of constrained equations modulo gauge symmetry. In the supergeometric language, we are looking at the zero locus of Q in the bulk, and we are transitioning to the leaf space of the distribution induced by linearization of Q on its zero locus, and likewise for the bulk. So it's a moduli space of the DG manifold, differential graded manifold. So you can consider it for the bulk and for the boundary. So you can do it for any gauge theory, but here the answers are particularly simple. You just obtain the Ramk homology for the bulk and for the boundary. And the projection from bulk to boundary here gives a map, which is not anymore surjective. In fact, the image of this map is Lagrangian with respect to the symplectic structure on the boundary. So here, well, this can be understood as sort of reduced phase space. It's symplectic. Symplectic structure is the Poincare duality. The bulk object here is a degree is Poisson. It's not symplectic. It's Poisson with degree +1 Poisson structure. And in fact, the symplectic foliation of this Poisson manifold is given by fibers of this map. And in fact, this picture persists to essentially to any gauge theory in BV-BFV formalism. So you can consider such moduli spaces. They will be more complicated generally, but still you'll have this structure with some map with a Lagrangian image, and its fibers give the symplectic foliation for the natural Poisson structure for the bulk moduli space. For instance, for non-abelian Chern-Simons, this gives you interesting deformations of these objects. You will have certain natural supergeometric thickening of the moduli space of flat connections for the bulk and for the boundary. Okay, and yeah, so this kind of image of the bulk object in the boundary object has so it's called the Evolution Lagrangian. So it encodes the data of the evolution of the system, of the dynamics of the system. So restrictions of, so in this case, those homology classes on the boundary that come from solutions of equations of motion in the bulk. Okay, so now towards quantization. So the quantum version of the BV-BFV package is like that. So to an n-1 dimensional closed manifold, we would assign a cochain complex, so a space of states with certain differential, denoted here omega, which is quantum BRST operator. To an n-manifold with boundary, we would assign two objects. So one is the space of residual fields, which is some finite dimensional odd symplectic vector space, and a partition function, which is an element of the, tensor product of the space of states for the boundary and functions of residual fields. So, the main kind of structure relation is a quantum master equation modified by the boundary term. So, in the absence of boundary, it's just the usual quantum master equation that the partition function is killed by the BV Laplacian on residual fields. But in presence of boundary, this differential is changed by this boundary differential. And in the absence of residual fields, this is sort of the quantum statement of gauge invariance that omega kills the partition function. And here we have sort of a mixture of both. So in fact, this whole formalism is sort of a mixture of the idea of effective BV action and idea of a, idea Siegel's idea of the answer for a bulk manifold as being a vector in the space of states attached to the boundary. And gluing here, gluing of two bulk manifolds over some interface corresponds to evaluating a pairing inside the space of states for the interface. So one remark here is that the space of residual fields can be chosen in a variety of ways. So there's a partially ordered set of realizations. And here, maybe we could remember that picture with like sparse triangulations and dense triangulations and sort of the final object corresponding to cohomology a few slides before. So there are different realizations for triangulations. There is, for different realizations of residual fields. There is certain minimal realization and sort of larger realizations. And you can always jump from a larger to a smaller realization by each arrow here is kind of a symplectic fibration, and you can always jump from a partition function for a larger space of residual fields to a smaller space of residual fields by integrating out redundant fields, so by a fiber BV integral. And the kind of the very rough idea of quantization is like that. So if you are given a classical BV BFE theory, how to construct a quantum one out of it. So the idea is that, well, first you actually equip your boundary space of fields or boundary phase space with a Lagrangian polarization. And for simplicity, let's think of a real vibrating polarization with base B curly. So, and we want it to be such that this boundary one form vanishes along the fibers. So one can think of it as a very simple example of geometric quantization. So the space of states here would be functions on the base. Actually, yeah. So here I'm sort of a little bit simplifying the picture. So it should be half densities really instead of functions. But let's drop those details. So roughly speaking, functions on the base, and well, the differential is constructed as a quantization of the boundary BFV action, and well, hoping that we can construct a quantization which squares to 0. Now, so we look at the fiber of the composite map from the bulk fields to the boundary fields and then down to the base of the polarization. So let's call Y this fiber. Then we want to split this fiber into a slow part and a fast part and integrate over a Lagrangian in the fast part. So that is this partition function Z. So it depends on two things: on a point in this base, or in other words, in a Lagrangian inside the phase space, which is one of the family of Lagrangians giving me the Lagrangian polarization. So it depends on this little b, and on a point in the space of residual fields. So given such 2 points, I can integrate over Lagrangian in Y prime, and well, I get some number. So that's the value of this partition function. So it is indeed an element of the space of states tensored with functions of residual fields. So this is the idea. Okay, so this is the very rough idea, but so then there are examples where it can be made precise and where one can check explicitly how the kind of the axioms of the quantum BV-BFE package work out. And here's the class of examples. So this is a subclass of the famous AKSZ sigma models. AKSZ stands for Alexandrov, Kontsevich, Schwarz, and Zaboronsky from the famous paper of 1995. So the main construction is hidden in the middle of a paper in one paragraph, as far as I remember. Here we want to, but essentially those are kind of theories where the space of fields is modeled on the space of differential forms, non-homogeneous differential forms. And also the quadratic part of the action is given by, corresponds to the de Rham operator. So those are kind of the important features of AKSZ theories. So here I want to focus on the subclass, which we call BF-like AKSZ theories. So the space of fields is two copies of differential forms on a manifold M, which is a manifold of some dimension n. And first copy tensored with some graded vector space of coefficients. Second copy tensored with a dual space with appropriate degree shift. Again, I call these two differential forms A and B. So the action is, well, BdA, so the kinetic term plus some potential term, which comes from a function on the cotangent bundle of this coefficient space V with a degree shift. So I want to pick some function which satisfies a consistency condition, which looks like Poisson bracket of F with F vanishes with respect to the symplectic structure on this cotangent bundle. Then I want to evaluate, so this is my potential F or KZ potential. I want to evaluate it on this pair of differential forms. So instead of the base coordinate, I plug A, instead of the fiber coordinate, I plug B. So evaluate it on this pair of differential forms and then integrate. So that's the AKSZ action. And provided that this consistency condition happens, this action satisfies the master equation. All right, so one can easily write down the kind of the full bulk and boundary packages, the classical BV-BFE packages. So the boundary data actually is given by same formulas as boundary data is given by same formulas as bulk data, just replacing M with sigma, with the boundary sigma. Now for quantization, I want to kind of think of some manifold with boundary where some part of the boundary is called sigma A, and some part of the boundary, the rest of the boundary is called sigma B. And I call them like that because I want to fix a polarization with base given by the A field on sigma A. So essentially, I will be wanting to fix the boundary condition for the A field on sigma A and fix the boundary condition for the B field, fix the value of the B field on sigma B, and ignore the A field on sigma B, and likewise ignore the B field on sigma A. So, and these boundary conditions, I call them A and B with double leg. So then, okay, so the space of states on sigma A, so that would be just the space of functionals on of the A field, which is this differential form on the A boundary. Or I can also think in terms of some more explicit model of which functionals. I mean, this looks like a huge space. It's of the size of a space of functions on the space of differential forms on some manifold. So it's enormous. So a slightly more kind of manageable model is to think in terms of special kind of functions, where I think of, well, considering a bunch of well, K points on the boundary. So evaluating my A field at those points, and then contracting with some wave function, which is dependent on those K points, and well, integrating over the configuration space of K points. So in this sense, I'm considering some states given by some wave functions. So K point wave functions. And similarly for the B side. Now, the next point is that the fiber over a boundary condition here is given by differential forms vanishing on the A boundary or relative to the A boundary for the A side, and differential forms vanishing on the B boundary for the B side. And the corresponding smallest version of residual fields is given by just the RAM cohomology of the space upstairs. So it's relative cohomology of M relative to the A boundary with tensored with V, and cohomology of M relative to the B boundary tensored with V star. And I call this an element here, a pair of homology classes, little a and little b. So then the partition function is, okay, it depends on the boundary fields. So kind of a non-homogeneous differential form A here, and non-homogeneous differential form on the B boundary, the B with double leg, and on this pair of classes, little a and little b, a pair of relative homology classes. And the formula is like that. So it's a Raysinger torsion of M relative to the A boundary raised to some power, the negative superdimension of the coefficient space. And then a sum over diagrams And so the contributions of diagrams are like that. So it's h bar to the power negative Euler characteristic of the graph divided by the number of automorphisms times the integral over the configuration, the space of configurations of vertices of my graph. On M of certain differential forms. So here graphs are, so this is an example of a graph. So it has some bulk vertices, some boundary vertices, and the graph is oriented. And it has also leaves for the bulk vertices, and the boundary vertices are univalent. So I'm thinking of this vertices as being able to travel everywhere on the M as long as they don't collide. And also boundary vertices can travel on their own boundaries. So the space of their positions is the configuration space. Actually, I can transition here to the Fulton-McPherson Axelrod-Singer compactification of that configuration space. It's actually the integral of a compactified configuration space. And well, the object that I'm integrating is, okay, it's a product of some things. So for each edge, I need to put a propagator. And a propagator is a certain n-1 form on the configuration space of 2 points, which correspond to the, well, positions of the 2 endpoints of the edge. I will say a couple of things about a propagator in a second. So, and then for each edge, for each boundary vertex, I should put like form A at that point, or form B at that point, form B at that point. And then for each leaf, I should put just a copy of the corresponding homology class. So, and then this all is getting multiplied by just a contraction of Taylor of the vertex tensors that come from Taylor expansion of the potential F. So that part doesn't depend on the positions of vertices, but just depends on the combinatorics of the graph. So just a contraction of the Taylor coefficients of F given by the combinatorics of the graph. All right. So now a couple of comments about the propagator. So, well, a propagator is supposed to be the integral kernel of a chain contraction from differential forms vanishing on the boundary to the image of cohomology relative to the boundary. So it is an integral kernel of that linear map. And there are lots of such linear maps. There's a contractible space of such linear maps. And so there's lots of choices for a propagator. So another way to characterize the propagator is that it is a form which is nearly closed. It's a n-1 form on configurations of 2 points, which is nearly closed. I should emphasize on the compactified configuration space of 2 points. So in fact, D of it is representative of the relative Euler class of M relative to the A boundary. So you can write it in terms of some fixed, some chosen basis in cohomology, in relative cohomology. So the other property is that, well, if you fix one leg of the propagator and you integrate the other leg in a small surface, small sphere, tiny sphere around the fixed leg, then you get 1 in the limit of the sphere getting very small. So, and then the other properties are the boundary conditions, that if I fix the first leg of the propagator on the A boundary, it should be 0. And if I fix the second leg of the propagator on the B boundary, it should be 0. And that's it. So that characterizes the propagator. And well, there are kind of various constructions of propagators. And for instance, if you are given a Riemannian metric on the manifold, you can construct a Hodge type propagator out of it. So, okay, so now I explained what is the partition function. I want to say what are the differentials, this quantum Biaresti operators on the spaces of states. So, so they are built from codimension 1 boundaries, so from codimension 1 strata of the configuration spaces of points on M, corresponding to a collapse of a subgraph near a point on the boundary. So this is a picture for the case of the A boundary. So we have some kind of collection of points collapsing near the boundary. So this is kind of a zoomed in picture where we're thinking of a bunch of points collapsing near the boundary. And well, this arises from, well, some subgraph of a Feynman graph collapsing near the boundary. So these pictures, so they should be evaluated as configuration space integrals in this upper half space, and they give a polynomial expression in A and in derivatives in A. So what you obtain is some complicated higher order differential operator in A, which is in this boundary field, and with complicated coefficients given by configuration space integrals. And well, in fact, this construction satisfies the property that these two differentials for the A boundary and for the B boundary, they both square to 0. This is a non-trivial statement, but it comes from a careful analysis of configuration space integrals and kind of boundaries and corners of the configuration space, and from the Stokes theorem on the configuration space. And sort of by a similar technique, one proves the quantum master equation modified by the boundary term. That's the partition function given by bulk Feynman diagrams is annihilated by the sum of these two differentials on the A side and the B side, and this Laplacian acting on the, so this is essentially sum of d over dA, I don't know, I d over dB, I. So it's a second order differential operator in this relative cohomology classes. So this is again an application of the Stokes theorem on the configuration spaces. And this is the same technology, or kind of, yeah, it's an application of the same technology as the one used by Axelrod and Singer in the papers on perturbative Chern-Simons theory and in Kantsevich on deformation quantization. So the technology of the Stokes theorem for configuration space integrals. So another property that holds in this construction is gluing. Namely, if I have a manifold M1 whose B boundary is coincides with the A boundary of a manifold M2, then I can glue them together. And the partition function for the glued manifold can be recovered from partition functions for the two pieces by integrating out these two interface fields with this Fourier kernel. In fact, if I had the partition functions for the two pieces calculated using some particular propagators, let's say eta1 and eta2, then this corresponds to calculating the partition function for the glued manifold using some particular propagator, some kind of gluing of eta1 and eta2, which is, well, I tried to draw some picture about how it is constructed, but in particular for this glued propagator, if one leg is on M2 sides, the other leg is on M1s. Oh, I guess I confused the indices here, sorry. So if one leg is on M2 side, the other leg is on M1 side, then this glued propagator is constructed out of the eta1 and eta2 by putting some intermediate point and considering eta1 between that point and x1, eta2 between x2 and that point, and integrating over that point. In fact, this construction gives you a propagator. So, okay, so yeah, so in fact, Feynman diagrams on the glued manifold, they come from Feynman diagrams on the pieces. So in fact, you should just look at how the interface cuts the Feynman diagram, and that tells you how it is assembled out of Feynman diagrams on the pieces. For instance, this theta graph diagram on the glued manifold, which is a two-loop diagram, is in fact coming from a gluing of two zero-loop diagrams on M1 and M2. So given by this, okay, single bulk vertex and three boundary vertices in each case. Okay, so now kind of some example in non-abelian BF theory. So this is an example of this class of AKSZ models corresponding to the coefficient space being the Lie algebra shifted by one, and with this potential coming from the Lie bracket in the Lie algebra. So here the one can calculate explicitly the boundary differentials, and they have this kind of free term, for instance, for the A side, plus a correction coming from this diagram. So there's only one boundary diagram, and it's easy to calculate. And it's a first order differential operator in A because there's only one outgoing edge. And likewise for the B boundary, you have kind of a free term and a correction coming from this diagram. So there are two kind of edges going outside, and that corresponds to the fact that this is a second order differential operator. All right, and the more complicated example is two-dimensional Poisson sigma model responsible for Kontsevich's deformation quantization in particular. So here you have M, a surface with boundary. The coefficient space is a dual with a shift by one of a vector space equipped with the Poisson bivector. So the action is like this. So it's again a perturbed BF action, so the free term plus a potential term given by the Poisson bivector. And here, well, okay, the partition function is given by this general formula with graphs on a surface. But I wanted to say something about the boundary differentials. So in fact, it turns out that the boundary differential on a B side can be written as a canonical quantization, or standard ordering canonical quantization, so all derivatives to the right, of the following object, which looks almost like the boundary BFV action in this model, except that I should replace the Poisson bivector with its complicated deformation, which comes from the star product. This is a deformation written in terms of the Kontsevich's star product, and it has all the H bar corrections, and it actually involves all the Kontsevich's integrals over the upper half space, over configurations of points in the upper half plane. So yeah, and those are precisely the integrals that appeared in this construction, in the construction of the boundary differentials. All right. So that is what I wanted to say about that class of AKSZ examples. And now I wanted to talk about another application of the formalism, and that is to two-dimensional Young-Mills, which is nearly an AKSZ theory, but so it's nearly non-abelian BF theory, but perturbed by an additional term which involves a fixed area form on a surface. So fixed area form on a surface times the kind of the pairing of B field with itself. So here I'm thinking of the Lie algebra as being corresponding to a compact group. So it's equipped with some killing form. So I can, using it, I can pair the B field with itself. So I can identify G star with G and pair B with itself. So this is nearly a AKSZ theory, except that it depends on this additional piece of source geometry. So a fixed area form. So the boundary structure here is exactly the same as in non-abelian BF. So that part just doesn't notice the area form at all. In particular, the space of states on a circle with A fixed polarization is functions of the A field on a circle with the differential that I wrote a couple of slides before. So this differential, and you can calculate the cohomology of this differential. So the zeroth cohomology is the space of class functions on the group, which I'm mentioning because this is a kind of a standard object in the sort of the discussion of 2D Young-Mills theory. So as a reduced space of states for the 2D Young-Mills, the space of class functions on the group, which has a nice basis given by characters of irreducible representations. Okay, so now the problem that we considered with Ricardo Iraso was that we wanted to obtain a closed formula for the partition function on, well, let's say on a closed surface from a direct perturbative computation. And well, the challenge here is that, well, this theory has lots and lots of Feynman diagrams, and they also multi-loop Feynman diagrams, and they correspond to complicated configuration space integrals. So how can one hope to calculate all of them and assemble into some sort of some closed formula is completely unclear. But so the idea is to use BV-BFE formalism and to cut the manifold M into some convenient pieces, building blocks, which admit some convenient gauge fixing, for instance, axial gauge for the cylinders, where all Feynman diagrams can be computed explicitly and resummed. So yeah, so the idea is to compute all Feynman diagrams on those cleverly chosen pieces and then reassemble the partition function by the gluing formula. And then the statement that we obtained is that, well, one can do that. And then for the case of a surface with, well, either closed surface, a surface with boundary given by a bunch of circles in A polarization, we have the following, that we can assemble this building blocks into a partition function for the whole surface. Then it will depend on residual fields. We need to take the BV integral over residual fields, and then transition to the to a class in the cohomology of the space of states for the boundary circles. So that's denoted by this square brackets here. And the result is this wonderful formula, which is known in the literatures as a non-perturbative answer for 2D Yang-Mills. So that's coming from, well, Migdal and Witten. It's a sum over irreducible representations of the group, so compact group, of dimension of the representation to the power Euler characteristic of the surface, then a term involving the area form, in fact, the total area of the surface. So it's exponential of the total area times the quadratic Casimir, and a term involving the boundary circles. So the nth power of this basis element in the space of states coming from the character of the representation R. Okay, so I wanted to say just a couple of things about this development. So, yes, so for instance, well, a surface can be cut into a sphere can be cut into these building blocks. So these two cylinders and these two disks with B boundary, and it's a useful trick to concentrate the area form only on one of the cylinders, namely on this AB cylinder. And well, one can show that the answer into the Yang-Mills, you can kind of concentrate your area form wherever you like, as long as the total area remains the same. So in fact, for all these building blocks, you can calculate explicitly the partition functions, and you have only 0 loop and 1 loop diagrams and nothing else. And for instance, yeah, multi-loop diagrams, for instance, this one on the sphere, they come from 0 or 1 loop diagrams on the pieces. For instance, this diagram comes from gluing these two diagrams on the pieces. Which kind of, these are parts of those computations that can be resummed. And if you want kind of to recover the answer for high genus surfaces, or surfaces with many boundaries, many boundary circles, you're forced to consider gluing and cutting with corners, which is an extension of BV-BFE formalism. So, and here, yeah, you can cut a surface into, well, for instance, triangles or some polygons with A boundaries, and insert this kind of beams with B boundary in between the edges. And these polygons, themselves, they are assembled out of this, essentially those disks and B disk and the special cylinders that also appeared here. And in this context with corners, also there's a polarization carried by the corners, either A fixed or B fixed, which I denote alpha or beta polarization. So in this context with corners, so the arcs are assigned A or B polarization, corners or vertices are assigned alpha or beta polarization. So you have spaces of states also for corners. And for an alpha corner, the space of states, so actually the spaces of states, they are DG algebras. And there are two versions, alpha polarization or beta polarization. So for an alpha corner, we have the functions on the alpha field, which is the zero component of the A field there, which is a ghost field, which is just the Chevalier-Eilenberg cochains of the Lie algebra with its Chevalier-Eilenberg differential and also with a wedge product. So it's a commutative DG algebra. And for a beta corner, it's a bit more complicated. So naively, you have functions of the B field at that corner, but in fact, it should be considered with zero differential, but non-commutative product. So in fact, one needs to deform the product there, and it should come with actually a deformation quantization of the commutative product. So it should be actually the universal enveloping algebra of G with non-commutativity weighed by H bar. So one can look at those two constructions as sort of geometric quantization of the corner phase space with two possible polarizations. And so, for instance, then I can disassemble a boundary circle into corners and arcs, and then the space of states there will be a tensor product of arc spaces, which are bimodules over corner spaces, which are algebras. And the differential for this circle is assembled out of pieces. So there are pieces corresponding to arcs, which are given by formulas we've seen before, corresponding to corners, which are given by, well, these two formulas, so Chevalier-Eilenberg differential or zero, and some interesting contributions corresponding to pairs, corner, comma, arc. And these are interesting high infinite order differential operators that also involve Bernoulli numbers. So the picture one has here is essentially the picture of Bayes-Dolan-Lurie extended TQFT. So where you have to a point you assign DG algebras, to arcs DG bimodules, and to two cells some, well, area dependent morphisms of DG bimodules. So, and here you have the quantum mass equation for surfaces with corners, and you have two kinds of gluings. So gluing of arcs at vertices given by the tensor product of bimodules over an algebra, and gluing of regions over arcs. So that is what I wanted to say about 2D Young-Mills and kind of its extension to corners, which is which was forced on us by just wanting to calculate perturbatively the answer for even a closed surface of higher genus. And the final thing that I wanted to say is another application of another example of essentially effective BV actions with boundaries, and that's for Chern-Simons theory on a cylinder interval across a surface. So let's look at the non-abelian Chern-Simons theory. So in BV formalism, so the field here is a non-homogeneous differential form with components in the RAM degree 0, 1, 2, and 3 being the ghost, the connection, the anti-connection, the anti-ghost. And I want to think of the space of fields specifically for a cylinder as forms on an interval with values in forms on a surface. So I want to think of this theory as sort of a one-dimensional theory with an infinite dimensional coefficient space. So, and then fixing some particular polarizations on the boundary with ghost fixed and 0, 1 component of the connection fixed at one boundary, and the ghost fixed and 1, 0 component of the connection fixed on the out boundary. So here I'm talking about 0, 1 and 1, 0 components that's relative to some fixed complex structure on the surface. So in the setting, there is some minimal space of residual fields, which is just given by, okay, looking at the fiber over the boundary condition and transitioning to the cohomology of the RAM operator on the interval. So that gives you the following model of residual fields, which is just cohomology of the interval relative to the boundary points with coefficients in 0 forms on the surface, plus absolute cohomology of the interval with coefficients in 2 forms on the surface. So I call this cohomology classes, so sigma. So that's just a mapping from sigma to the Lie algebra, and a star, which is a 2 form on sigma with coefficients also in the Lie algebra. And the ghost numbers are 0 and -1 here. And this is a 2 form, this is a 0 form on the surface. All right. So then there's a computation of the effective action, which is well, there are kind of several families of Feynman diagrams to compute, but actually it's manageable. So there are, okay, several sequences, but they're at most one loop diagrams. There is some answer that you get here, which might look a little bit intimidating, but actually transitioning to a convenient parameterization of the space of residual fields, namely the group parameterization, so the exponential of the sigma field and some reparameterization of the second residual field, so that together with this group field, they form a Darboux pair. So G is a mapping from the surface to the group. Then what we get is something that at least parts of it look familiar. So you get the Versumino-Witten action of evaluated on this group valued field on sigma, plus some terms where that group field interacts with boundary conditions, and well, terms where G and G star, so both residual fields in the bulk, interact with boundary ghosts. So this first line here, one can recognize the gauged or G over G Versumino-Witten action. And here it's sort of supplemented with some boundary terms, ghost terms. So, and the principal field comes as a residual field in this picture. So here one has the master equation, and for that it's very important that we didn't forget the ghost terms for some natural boundary differentials. And in fact, one can say that it's equivalent to Polyakov-Wigman formula for the WZW action. So let me not comment on this. There is some kind of classical symplectic geometry interpretation of the answer, of the procedure of computing the BV integral here. But I wanted to just very briefly say that this is a part of the following picture. So we have this cylinder with boundary conditions I talked about. The effective action is the partition function gives this gauged WZW enhanced with ghosts. If you pair with two particular boundary states, namely putting all those boundary fields to 0, you get the pure WZW. Now you can also consider the same story, but with 1-0 polarization on the in boundary, everything else the same on the out boundary. Then there are more residual fields in this story. There are some additional residual fields. You can again calculate the effective action. In some convenient parametrization, it's some other slightly bizarre version of WZW theory. So with some additional, so if you forget about the boundary fields, then it gives sort of the G left or G right gauged WZW, but then also interaction with the boundary fields. So this is what I call WZW twiddle here. And one can also glue the ends of the cylinder. And then it's a Chern-Simons on a circle across the surface. Then there are a lot of zero modes here. They just homology of the circle tensored with differential forms on the surface. Well, the zeroth cohomology I call here A straight, and the first cohomology I call B straight. And the effective action here is easily computed, and that's two-dimensional BF theory in Batalin Vilkovisky formalism, with some interesting caveats that there are unusual large gauge transformation acting on the B field. So that's what sometimes is called compact two-dimensional BF theory. And then this all sort of fits into this picture that there's this master object, this WZW with a twiddle, and one can glue the ends there and obtain 2D BF theory. And one can sort of go this side by doing the Siegel-Bargmann transform, so changing the polarization and integrating out the residual fields. And then if you pair with the special boundary states, you get WZW theory. So I wanted to say that this is sort of a connection between the dimensional reduction for Chern-Simons and sort of the holographic counterpart, holographic dual of Chern-Simons. So, and the connection is through this intermediate object. And since I'm out of time, I just wanted to kind of show this slide, but not comment on it much. There's an example which works somewhat similar. It's also a Chern-Simons theory on a cylinder, but now on a 7-dimensional cylinder, an interval cross a Calabi-Yau threefold, and instead of WZW, you have the BCOV theory, or Kodaira-Spencer gravity. It's another name for it. I'm sorry, I'm out of time, and thank you very much for attention. Thank you.
Thank you very much for your talk. Are there any questions?
Hi, Pavel. Thank you for the talk.
Oh, hi. Hi. Thank you.
So my question is, here with the Chern-Simons on a cylinder, the sigma has no boundary, right?
Yes, sigma has no boundary. Yeah.
So is this just for simplicity right now, or I mean, have you thought about the case where sigma has a boundary?
So it is for simplicity right now, and actually, yeah. So this is something that this is sort of a thing in progress. What I was explaining in this picture, but yeah, one can sort of iterate with yeah, one can consider the story with corners and sort of iterate or the story of dimensional reduction and well, effective actions, because yeah, for a 2-dimensional BF, putting some clever boundary conditions, there is sort of another holography story which links it to the particle in a group, right? Particle in a group. So yeah, essentially considering the story with corners, as you say, yeah, one can sort of consider 2 arrows one after the other. So, and it's an interesting discussion. I didn't feel ready talking about it.
Okay, thank you. I have another question, just brief one. So, I mean, I suppose you're sort of in a very topological mindset here, and the boundaries are just boundaries without sort of any different type of boundary. But if you want to, maybe I should have asked this yesterday to Nicola, but if you want to think about something like Lorentzian.
Oh yeah, yeah. No, so in fact, here I should refer to, so that there are papers written by Cattaneo, Schiavina, and Canepa. So on gravity in this context, and then for them it's really important. Lorentzian, so yeah, the signature of the metric restricted to the boundary, or whether it's degenerate or not. So that becomes extremely important. Absolutely.
Yeah, no, I just want just a very simple point on that. Just if you have a Lorentzian thing, or you want to compute in the Riemannian setting and then maybe analytically continue to the Lorentzian setting, I think I'm just curious. You probably need to distinguish boundaries that are time-like and those that are space-like. And I'm just
yes, that is absolutely true. So well, here indeed I was sort of in a topological mindset, and the metric, whenever I would be using it, it would be for gauge fixing, and for gauge fixing I wanted to be really Riemannian, to have sort of good ellipticity properties and to have Hodge decomposition. So and this would be kind of messed up if I'm allowing Lorentzian signature, but yeah, still, of course, one can play with Lorentzian signature, and then yeah, as you say, the signature of the boundaries will become very important. Yeah, I don't know how to. Oops! Oh, sorry, I did something bad. The signature of the boundary becomes very important in the setting. I'm not sure they can kind of comment meaningfully here. Sorry, my share disappeared, right? Oh, okay.
So hi, Pavel. Wonderful talk. So I was wondering when.
Oh, sorry, I don't hear too well. The sound is sort of garbled.
I was just wondering when you can say something similar instead of for Chern-Simons, the current sigma model.
Oh, right. So, well, that would be very interesting. So, sorry, who am I speaking to? Ah, yes. So,
Michael.
So that is a very interesting question, and here I actually, yeah, I would like to be able to say something about current sigma model in this context, but I'm not ready. And here I want to say that there's a very nice recent paper by one of the speakers at this conference, Miquel Cueca and Alejandro Cabrera, where they are saying something interesting about current sigma model and its sort of, well, using sort of different technology and its kind of two-dimensional reductions. I think there is some conceptual difference in how we are treating sort of a three-dimensional theory, sort of as a theory on an interval with values in something on the surface versus something on the surface with values in something on an interval. So in which order do you do the adjunction? Yeah, I'm not ready to say to say anything about current sigma model, but I'd love to. So that's everything I can say.
So maybe, do you think that in the current case, some similar propagators can work, or?
Oh, propagators for sure. I mean, propagators, they just come from the abelian story. And here, kind of this Chern-Simons theory is seen as a deformation of an abelian Chern-Simons. So for all these objects, you can write the abelian counterparts, and they should be the same, at least as current sigma model looked at locally on the target.
Oh, okay. Thank you.
Mm-hmm.
More questions, comments? Online or in Freiburg? Okay, doesn't seem to be the case. Then we can thank our speaker again.
Thank you very much. Thank you. All right.
And yeah, so the plan is to have now a 15-minute coffee break. So coffee in Freiburg and breakout rooms online. And afterwards, there will be no more Zoom, but we all meet